Welcome to Computer Vision Decoded. I have a really exciting episode today. We're going to talk about computer vision in the wild. We're going to be joined by our co-host, Jared Heinly, a computer vision expert, and he's going to talk about past academic experiences he's used computer vision in the wild, where he's got photos from all sorts of random sources and how he managed to do 3D reconstruction with these images. We're also going to dive into some more practical use cases for you at the second half of the show, where you can learn better how to create 3D reconstructions of various scenes using different cameras, and having different sorts of situations around you and always be successful. So I hope there's something for everyone here, and let's jump into it with Jared Heinly. Welcome back, Jared, to episode 3 of Computer Vision Decoded. Today we're going to talk about reconstruction in the wild, 3D reconstruction in the wild. And I wanted to start off by talking about some of your past experiences. And these are experiences that you had both in your academia and professionally here at EveryPoint. So I just want to start off more in your academia, the projects that you worked on prior to joining our team and making a huge impact in our world. So with that, the first project I want to talk about that has to do with 3D reconstruction of objects using images in the wild was a project you had for correcting the duplicate scene structure in Sparse 3D reconstruction. And that's the title of one of your papers that you worked on. And just to start off, for people who aren't from the computer vision world, can you tell us what Sparse 3D reconstruction means?
Yep, happy to. So a Sparse 3D reconstruction, it's different than a dense 3D reconstruction or a mesh in that it is much more sparse. So the main outputs of a sparse 3D reconstruction are your camera poses. So for each image that's in that reconstruction, you'll have both its position and orientation that was determined, as well as some set of typically 3D points that are in the scene, that are points that represent to points that are like of objects in the scene. And so what you might look at is you'll end up with this point cloud that some objects you may see very clearly, but other objects may be sort of a bit sparser, and the points aren't going to be regularly distributed over the objects. It's not going to be like points on a regular grid. It's these points, to even get more into the details, it's points that came from key points that were extracted in the images. So for each image that's being processed, there are typically thousands of key points that are extracted, and it's those key points that have been triangulated in the scene. It's those triangulated key points that are that sparse point cloud. So it's a sparse set of points plus camera poses.
Okay, that really helps set the scene for this topic and the next. So what is the challenge? It's for correcting for duplicate scene structures. So when you say duplicate scene structures, that's, in my understanding, that is perhaps you see a building and you'll see the exact same archway or exact same window set over and over. Think of a garage door. You got the same like kind of square rectangle on the front. So what's the challenge with that? Why in computer vision and generating a 3D model of a scene with those repeating features? What is that happening? What's happening to the algorithm that is causing issues you have to correct for?
Yeah, no, definitely. So the problem with the sort of duplicate or repetitive structure is that, it's confusing for computer vision because it looks the same from different photos. So it's the same, I shouldn't say it's the same. Different parts of the scene have the same appearance. And so the computer vision code thinks that it's the same thing even though it's different. So for example, a classic data set that I worked with was Big Ben in London, so the famous clock tower. And if all four sides of that clock tower look essentially the same. And so if you have a photo of just the front of the clock tower and then a photo from the back and you show it to a human, they're not going to know the difference. And same thing with the computer. The computer's not going to know, hey, that these are from different sides. If all that it sees is the clock tower face, it's going to say those look like the same thing. And so when it tries to compute the camera pose, like the position of those images, it's going to think that they're from the same side of the clock tower, as opposed to distinguishing that no, these are separate. And so what can end up happening is if I have images from different sides of that clock tower, from the front, the left, the right, and the rear, all of those can sometimes be collapsed into a single reconstruction. So all 4 sides end up being reconstructed as one, and it thinks that all the photos were taken from one side of the clock tower. You can imagine this too, like you said, okay, the example of a garage door. If you have a garage door that has like the same repetitive windows or the same repetitive pattern across it, if you had photos that only showed 1 or 2 segments of that repeating pattern, what could end up happening, as opposed to reconstructing your entire garage door, some of that could collapse where it thinks, oh, the left side's the same as the right, and all of those get overlaid on top of each other. And so it's this issue of, when the computer is looking at a photo, trying to identify the key points, trying to identify the texture and the colors and the patterns that it's seeing in the image, it's looking for those same patterns in all the other images. And so when it finds a match, it wants those to be the same. Whereas in the real world, no, these are actually separate instances. Just as in one other example, here I'm talking about objects, Big Ben, where it's the same pattern on all 4 sides, or a garage door where it's the same pattern across that door. A similar class of challenges is when you have the same object in different parts of the scene. So if I had the same sign, like a no parking sign, and that same no parking sign is at different places throughout the city. If I just try to naively say, hey, well, let's match these images together. If they have the same sign in them, computer vision might think that I'm at the same location, even though it's the same sign at a different part of the city.
Interesting. Okay, so you're basically saying the computer gets really confused because humans, as we walk around a scene, we know we've moved, but a computer system, machine vision, might not know it's moved. There's no data saying, hey, I'm over here now. It's trying to figure that out from just the pictures how far it's moved. So what techniques is there different? You add additional data, perhaps GPS data, to let it know you've moved? Is that an option, or is it more an algorithm, the way in which you tell it to match images? What kind of techniques is there at your disposal?
Yeah, no, that's a great observation with the GPS. And there's a variety of techniques, and it sort of depends on what kind of data you're dealing with. So if you have images that are geotagged and have GPS information, you could use that as a prior. Use that as a way to help distinguish, that these photos, the GPS positions were a kilometer apart, but I think it's the same content. You can say, well, no, that doesn't make sense. But if your GPS said, oh, these things are 5 meters apart, okay, maybe that's more realistic, and then you could use that to help weed out those false positives, that weed out the incorrect matches. Mm-hmm. Other techniques could leverage, like you said, we as humans, as we're walking around a scene, we know that we've moved. So other techniques could leverage the fact that it's a video, and so as the video is moving, if I'm taking a video of that garage door and I see the left side, and I take a video as I slide over to the right, I know that going from frame to frame, I kept moving, maybe right, in the right direction as I come across. But then all of a sudden I'm like, oh wait, but the last frame of the video matches to in the first, and that would have been a leftward motion. But if I know that I was always moving right through that across the garage door, that just doesn't make sense. If I always move right, how can I end up moving left? So you can try to build in some of those geometric constraints. There's other sensor data that you can use to try to figure out what was the motion, and is this a plausible match based on the sensor data that you've captured. What I worked on in my academic work during my PhD was I was working on crowdsourced data sets. And so there I assumed, hey, there was no GPS data. I don't have videos, it's just images from all over the place. And so the technique that I used was to try to latch onto and leverage background scene content. So for example, in that Big Ben photo, the Big Ben example, sure, there's going to be some photos that only show the top of the tower, but a lot of photos are also going to show things around it. So like the nearby building, maybe some of the road, other buildings nearby. And so what I would say, well, hey, here's 2 photos that both show Big Ben, but the background content is entirely different. And so I would use that as a way to say, oh no, these are from different parts of the scene. Like this is from the front, this is from the back, based on that background scene content. But if I had 2 photos that both show Big Ben as well as similar background content, then I can say, oh yeah, no, this was taken from the same side. So using not only the parts of the image that match, but using the parts of the image that don't match, and the parts that were different also provides information about whether or not these photos were from the same area.
Okay, so I would just say this up front. Then it's important to know all the tools that you could have if you're building a computer vision pipeline, or you want to use it at, say for your job or for a hobby. Be careful of repetitive structures. So be cognizant, because you might have issues there. And B, do your research. Learn what these different methods you have. I know there's a lot of open source tools, even for people who are just trying to hobby it together, or contact people like us at EveryPoint. I know we've been working on this for a long time. So that just shows that computer vision sounds easy. But there's all these issues that can pop up that you might not know about going ahead into it. So this is a good one. I see this one all the time, especially around just scanning buildings. I've just noticed, especially there's a lot of repetitive window casings and things like that. If you like you said, if you crop in too far too, that can be the downfall, because you're losing some perhaps context around the scene that would have been much more helpful had you got that, as opposed to getting too close to the scene.
And that's a good point. And that's my biggest recommendation if someone's struggling with repetitive structure, has a scene that has a lot of repetitive structure in it. My biggest recommendation is just step back, make sure that your imagery is capturing more of the context of the scene. Those unique elements, because that's what's going to help provide better context to figure out where that image is placed. And just for clarity, when I talk about repetitive structure, you may think of like, a brick wall. It's like, hey, it's a wall, has a bunch of bricks on it. That seems like it's repetitive. And yes, it is, and that it's a wall made up of a bunch of bricks that are all somewhat similar. But each of those bricks has a distinct visual appearance. And, there's going to be sometimes there's, some mud or some dirt. And the computer, while to a human at a high level, you might say, oh yeah, that's just a bunch of bricks. The computer's able to see the differences in some of the patterns or the texture of that material. Same thing with like a pile of rock. You might be like, oh, that's just a pile of rock or a pile of sand. It all kind of looks the same. But it's like, well, no, there are like bright spots and dark spots. There is some variety in those patterns. Contrast that with, like you said, with windows and buildings, so man-made structures. Those can be some of the most challenging examples, especially new buildings made out of metal or concrete or white, where you have truly like the same window, is manufactured the same, installed the same in many different places. That's more the style of repetitive structures that I'm thinking about and talking about here.
That makes sense. Fortunately for all those archaeological historians trying to capture these 3D scenes, these little brick buildings in stone, it's just like no two bricks look alike. So that does definitely help. And you'll notice a lot of examples of brick buildings and things like that. They just, in my experience, I've never had a brick building have an issue like this. So.
Brick is perfect. That's a great reconstruction surface.
So I can imagine wood is too. So wood grains, things like that.
All
right. So stepping past this topic, then you kind of touched on the next project that you worked on that kind of takes what you're talking about here, this very small subject of repetitive structure, and you blew it up really big, world scale. In fact, it's called Reconstructing the World in 6 Days. That's a project that you had worked on, not just you, obviously, with a team. So I'm going to show, for people that are not listening to the podcast or actually on the YouTube channel, I will have just kind of a video playing as he talks, and he can talk about this video, but it's just showing some visuals of sparse reconstruction from this project. So it'll make sense when he starts talking, but I wanted to make sure that people saw that and knew what they were seeing here. So here, I'm put up on the screen. With this project, it was called Reconstructing the World in 6 Days. And can you just tell us about this project? Give us a quick background and what kind of, just start out there.
Yeah. So the goal of this project was really to see how can we process a massive data set of imagery and get useful 3D reconstructions out of it. So in this case, previous works had talked about, how can you process 3 million images, 4 million images, on a single computer, and get reconstructions out of it. So like, all of the images from Berlin, Germany, or all of the, not all the images, but a bunch of images from, different cities around the world. But it was at most, 3 million, 4 million, something like that. Whereas what I wanted to do was say, well, okay, why only 3 million? Why not 100 million? What sort of challenges do you run into when you have that big leap, in the order of magnitude of the data set size? And so the task of the project was saying, okay, how can I sort of scale up reconstruction techniques, scale up these pipelines and these algorithms to handle 100 million images, on a single PC, on a single computer, and get reconstructions out of it. And so what we're seeing here in the YouTube video is some of the sparse reconstructions from the different buildings and landmarks and scenes that were automatically discovered inside of these 100 million images. So from that 100 million images, automatically discovered over 12,000 different parts around the world, that people had taken enough photos of that I'm able to, generate a 3D reconstruction of it. So, Notre Dame, or the Eiffel Tower, Mount Rushmore, Big Ben, all these different landmarks around the world, as well as other kind of smaller, lesser known places, where there happen to be enough photos of it. But you can sort of imagine 100 million images from just, and they weren't sorted. Some of the images had geotags, but we didn't use that in processing. We just grab the first image, grab the second image, grab the third image, and sort of in a randomized order. And then trying to figure out, well, hey, have I seen, here's an image of a building. Have I seen this building before? Where, which other images is it related to? And trying to automatically group those photos together so that then they could be, turned into 3D reconstructions.
Mm-hmm. And so looking at this video, for people who are just listening to the audio, it's just a kind of a loop of different locations around the world, and you're seeing a bunch of black and a bunch of red dots. And so what we're seeing here is basically a very sparse structure of a landmark, and those black dots, that's the landmark, correct? And the red dots are where we decided the camera locations are, the camera poses.
Correct.
Interesting.
Yeah, and so those red dots are the camera poses, and the black dots, that's what I said before about like those triangulated sparse 3D points. That's what those black dots are in the scene. So you can kind of see a little bit of the structure.
Yeah, and as I'm looking at those aren't red dots. As you get in a little closer, you can see they're actually, I don't know the right word.
Little like pyramids or
pyramid shapes
or whatever.
And so those are where the cameras are and which direction they're pointed. And I know some are long, some are short, and that's just probably the different camera properties. Are they probably the lens or the
the focal length and
okay, so was the biggest hurdle for figuring this out? I mean, obviously you have cameras that got to be super grainy. There's got to be cameras that are, probably a lot of smartphone cameras because that's where people are doing. But this is also Flickr, and this was 2015. So also probably just a lot of cameras, point and shoot. So not high-end cameras.
Yep.
Was more issues you ran into? Did you end up dropping a lot of photos, or you only found out of those 100 million? Was it only a small subset of them? Obviously you probably had millions of photos of just kids and birthday parties and baseball games and things. Yep. But I'm assuming your biggest issue probably was trying to match the cameras and figure out which ones are actually the same scene.
Yep. Yeah. That was the biggest. So the biggest contribution of this project was figuring out, as you sort of browse, and work through. When I say you, I mean the computer. As the computer is analyzing all of these photos, which ones are of the same scene. When it's analyzing a photo, figuring out, hey, is this one, useful or not? And the way the method was designed was kind of interesting. It was a streaming fashion, and so it would load, a set of 100 images from disk at a time, process those images, figure out which ones were useful, and then discard, and then move on, load up the next set, process them, discard. And so it was sort of like an infinite processing engine where it could just keep loading data from disk, would process it, figure out where it went, and then would discard, and then it had some memory that it kept around as it found more images. But yeah, the biggest challenge is, as you said, like there's a lot of different kinds of cameras, a lot of different places all over the world, of both useful, interesting things like these buildings where there were a lot of photos, but stuff, kids' birthday parties, people just taking photos of their pets or the food that they were eating. I think there was someone had set up a camera that looked like it was like a time-lapse video of their aquarium, and there were like fish moving by or things like that. So there was just a bunch of just really diverse, varied imagery that, I might not have expected otherwise.
That one's interesting. Sorry, if you were looking on the screen, it was all the cameras were pointed up because they were doing like a fresco on the ceiling of a probably some sort of cathedral.
Yep.
And I've been to Europe and I know how it is. You get inside a cathedral and everyone just is looking at the ceiling because that's what everyone wants a picture of. If they let you take pictures inside.
Yeah.
So interesting. And so was this all done on one computer?
This was all done on one computer. A lot of it too was just getting good algorithms, and then just getting good engineering as well. So this was a single computer. At the time it had a pretty high-end CPU. I think it had 16 cores or something, which by today's standards you can go much further. Also, I was doing a lot of GPU computation, and so it had, I think, like 3 GPUs in the machine that I used for various operations. But yeah, it was a single computer in 6 days, and so that 6 days was sort of like the first 4 days were spent sorting through the photos, trying to figure out which ones were related to each other. And then the last, 2 days, it was more like a day and a half, was actually doing the 3D reconstructions of those different photo groups.
Mm-hmm. If you're on the YouTube, you can see this is interesting. They had the Statue of Liberty, and you can see there's a bunch of pictures close up, and all the pyramids are short, and then as the further ones away, they're probably from a boat or from shore across the water. So they all have these telephoto lenses. So they got these really long focal lengths. So you can almost tell what type of camera. Are they using a zoom camera, a zoom lens? They're using, a wide angle lens just by where they have to stand.
Yeah.
I think, very interesting. Yeah. All right. So we definitely established that you know how to use images in the wild, because obviously you have no control over these photos. Just these are a research data set that Yahoo at the time let people use for this sort of projects. A lot of amazing photos here. I'm going to just show another video here while it's still playing, but I'll flip over to this next one. And this shows the Pantheon in Italy, just kind of like a final, more of a dense reconstruction. And so can you just tell us what a dense reconstruction is for the few people who might not know?
Yep. So a dense reconstruction, still, at least in my case, I call it a point cloud. It's still a point cloud. There's still points in the scene. They're just much denser than they were in a sparse point cloud. So whereas in a sparse point cloud, each point corresponded to a key point in an image. So I have an image, maybe I extract a few thousand key points. And so if it's like a 12 megapixel photo, there's 12 million pixels. Out of that, I'm only selecting a few thousand of which, that are maybe like the corners of buildings or the corners of windows, or like blobs, or like a dark circle on a white background. So there's sort of these, highly unique, repeatable, recognizable points in the image. So the sparse point cloud is based off of that few thousand interesting points per image, whereas a dense point cloud or a dense reconstruction, each pixel in that image is going to contribute to a point in the scene. And so a lot of times use a different class of techniques, whereas the sparse point cloud is based on key points, a dense point cloud might be based off of depth maps. And so for each image, for each pixel in that image, you have a depth of where that pixel corresponds to in the scene. And so it's that can take that pixel and that depth, project it out. Now you have a point in the scene, and so that's what you can start to use to build up this dense point cloud, which just has, a bunch more points in it.
Yeah, interesting. Okay, so that makes a lot of sense. That's why if I play this one more time, you saw how much more dense that was.
Yeah.
That's you're trying to just maximize the number of features, and you typically see those textured meshes that people get for photogrammetry output as well. They're not using sparse; they're using a dense point cloud to get the geometry. Because instead of a few thousand, like you said, you can have hundreds of thousands, millions of points.
Yep.
And if they're dense enough, they look photorealistic.
Yeah, that's like a dense point cloud can look like a textured mesh just because the points are so dense. But those are separate things. Sometimes people start out with the point cloud and then turn that into a mesh. and then texture it, and now you've got a different representation.
So this example is also from crowdsourced photos. So
Yep.
That's what's amazing is, you can have not ideal conditions, and I'm sure the lighting inside this building is not super bright. You can still make it work if you have a good set of algorithms behind it and appropriate hardware configuration. All right, so last kind of real world application that you've dove into with images from the wild is at EveryPoint. When you joined our team early on, we still are building stockpile reports, which is one of our customers that does 3D modeling of bulk material piles at bulk material production yards. Think of like a rock quarry, or even salt piles for DOTs. Anything that's piled up in bulk materials, we measure it, and we turn it into, we capture photos or video of it, turn it into a 3D model, and we provide numbers to finance teams to do their business, and people running yards for operational decisions. So along with that, we have an app that lets the users walk around and capture imagery in the wild. And specifically for that use case, we're not caring about getting the best looking 3D output. We just want to get an accurate 3D model of a stockpile. And we have iPhones, we have drones, we have installed cameras. Those are cameras that are installed permanently in fixed locations. And I'm just going to talk about the first two methods, using an iPhone and using a drone. And what sort of issues have you seen that we've had to overcome with that? Especially with the iPhone, I noticed that we take video instead of photos. And I have a lot of people say, why aren't you taking photos? They're higher quality, they're higher resolution. And I'm taking this 1920 by 1080 video of a stockpile. Well, would I get better results if I took single images? So can you talk about when you're out there and you're in a situation where you're trying to collect useful data, not to get the prettiest looking 3D model, but trying to get one you can analyze and measure off of. And let's say you're trying to get a stockpile measurement, or you're trying to get the layout of a room for architecture design. Why did we go the video route? Why how is that helpful for collecting data in the wild?
Yeah, the video is helpful because it provides redundancy, and it sort of removes the burden on making sure that you've captured enough images. So yes, images are higher resolution, and so for some applications, when you're trying to get the most resolution and detail possible, an image-based data set could be better than a video-based data set. But at least in practice, in the kinds of reconstructions that I've done, having just additional frames beats resolution in many cases. And so you can imagine as I'm walking around with that video, if I'm recording 30 frames per second video, that's a lot of frames that I can pick and choose from to, use in the reconstruction. And so what's nice there is if I just had photos, maybe I walk around a stockpile and I only take 100 photos of it. And there's nice overlap between those photos. But if some of those photos maybe were accidentally blurry, or there was some sun flare, I may end up with part of those photos being unusable. And with those images being unusable, that's going to leave sort of big gaps in the reconstruction as I move around. Whereas with video frames, maybe only 2 or 3 video frames were blurry, but then that fourth one was perfectly crisp. And in that span of 4 video frames, we haven't moved very far. That's only a fraction of a second, and so we can use that fourth video frame in the reconstruction. And so you're able to leverage sort of the best video frames out of there, and sort of ignore the ones that weren't as useful. It's also just helped us with that redundancy, like if there are challenging environments. So in that case, like I said, with sun flare, if there is some sort of sun flare coming across the image, well, maybe we'll just extract more frames in that area, because as sort of the sunbeams move across the image, you can say, well, okay, I'll take a photo where the sunbeam was on the right, and then extract a video frame that was in the middle, and extract a video frame that was on the left, and so you can sort of dynamically select the best video frames to give you that good reconstruction.
And with how we've built it, that's not that's not a technician selecting frames. That's
Yeah.
just algorithmically combing through each image because a video is thousands of frames, not just a few hundred. And that's something I've noticed going out just anecdotally as I've played with these photogrammetry apps, and I'm just like, oh, I want to model the facade of this building in a really high detail, and I'll go out and with my iPhone's a great photo camera, or I'll use one of my mirrorless cameras, and I will take what felt like hundreds of photos, and then I go to upload them on my computer, and I have like 89 photos. So I don't think people realize to get a high number of frames, video is a great way to go, specifically too if, let's say, time is an issue. So I don't have a lot of time. These people who are doing going back to archaeological captures for 3D reconstruction of these famous scenes, they want it to be as accurate as possible, but they usually set up a whole day just capturing one small scene, or it might be a large scene, but they might be several days with the drone, high-end cameras, taking all stills, and they'll end up with massive amount of high-res imagery versus someone doing a stockpile or a warehouse. Maybe they need to capture a 3D scene of a warehouse. They don't have the luxury of 8 hours of taking photos. They need to move. They need to reconstruct it quick. Same with even self-driving cars using computer vision to see the environment around them. They have to get a lightweight, fast footage, fast output. So that's very interesting. As opposed to drones. So talk about drones. So drones, we're not taking video for the most part. I think we are taking video for specific situations, but majority of the users at Stockpile Reports, they're not using video. They're using camera still. So what's different? Why with the drone do I skip the whole, I'm going to take a video and I'm going to go straight to stills? What's unique about that situation?
Yeah, there I sort of see two different things. Like one is, and one of the biggest thing is that the drone, it's programmable in that we can program in a flight plan that we want, saying, hey, fly within this geographic region and make sure that as images are being captured, there's certain overlap, a specified amount of overlap between those images as it flies along a flight line, as well as when the drone turns around and comes back along a neighboring flight line, make sure that there's enough overlap between those flight lines. And so you can get very consistent imagery out of that drone because you're able to program it and have it follow that flight plan. Compared to a human who's trying to take photos, you might actually forget. You might think you're taking enough, but then, you turned a corner and you forgot to take enough photos as you turned and things like that, where the drone's just going to do it automatically. Another thing too is just, with the drone, a lot of times the drones are flying at 400 feet, and so you're just a lot higher, a lot farther away from what's being captured. And so yes, we could do it from video, and we get great reconstructions off of that. But sometimes just having that little extra resolution, at least higher than the 1080p video, is a little more useful there. But still, the biggest thing is just the consistency in capture. Does really help.
So I would say it in a nutshell or make it short. A human is terrible at capturing images. 70% overlap. If I said I need you to capture 70 or 80% overlap, I would be at a loss unless I've been really doing this for a long time to know what that looks like in image to image. Versus a computer, you say map out this territory. I want 75% overlap front face, along the track, and side to your next row of images be 60% overlap, and it's gonna pretty well nail that every time because that's what computers are great at, precision. Versus a human. And so you end up with a lot less images, but you'd only need the images that we tell it to capture, as opposed to let's overshoot and work our way backwards. So that's interesting. So as people are thinking of as well as capturing 3D reconstruction in the wild, that is a consideration. If I'm using an iPhone, or if I'm doing terrestrial-based scanning, or don't have a system to do interval captures at the right speed to get that overlap, because you do need a lot of overlap between images. That either programmable drone's good or go video. It just depends on which direction you're going to go. So that makes sense. And then we also have installed cameras. So instead of moving a camera around, now the cameras aren't moving, and we have a few of them, and that way we can we can capture high cadence of a scene. We can reconstruct the scene every hour, every 15 minutes, whatever interval we decide. You just trigger the cameras. What's completely different there? Because now we're going from thousands of images of a stockpile because someone on the site's just walking around with an iPhone, or you have a drone. They take off a drone, and it's going to take hundreds of photos, maybe even 1,000 if it's a huge site. Now you got 2, 3. How many images? What's the bare number of images can you use to get a 3D reconstruction?
Just need 2. As long as you have two images from different positions, you can use that to triangulate points in space and get our 3D reconstruction.
Interesting. And so, like, what are you thinking about when you put those 2 cameras up? Are you trying to get a high separation? Or is there like a sweet spot that you have to figure out? Is that all dictated by how far you can have it from a scene? What are you thinking about when you're trying to set up a system like that?
Yeah. So what I'm thinking about there is, and you hit it, like there's a certain separation that we're looking for. So compared to the other image-based or the video-based data sets where I'm going to have maybe hundreds of images observing that object, observing that scene, and have lots of redundancy. When I only have 2 photos, there it's like every pixel counts, and I need those photos to be as useful as possible. And so there we're looking for sort of a consistent triangulation angle. So it doesn't really matter how far away the object is. If it's 10 feet away or 100 feet away or 1,000 feet away. What I'm looking for is a particular angle. And so as the farther away the object is that I'm trying to reconstruct, the greater separation I'm going to have between those cameras and those images, ideally, so that I can get a nice angle that help me triangulate that point in space. So you can think about this as if my cameras were too close together. Those photos can look almost identical, and I'm not going to be able to distinguish, well, hey, how far apart really is that thing? Similar to how the human eyes work. Our eyes are spaced a certain distance apart, so that then we can triangulate points in space and sort of perceive depth. But that depth, as a human, perceiving depth using just the difference between our eyes, that only works to very limited range. After that, there's other spatial cues, and our brains doing all sorts of fun stuff to let us know how far away things are. But a computer doesn't have some of that. It's the computer is relying on that math and the trigonometry and the geometry to triangulate those points. And so there is sort of a sweet spot to know how far apart to put those cameras so that you get good triangulations and good reconstructions. Because if it's too close, images look almost the same, and can't perceive depth. And if images are too far apart, then the scene looks completely different, and it's really hard now to figure out which parts of the image are the same between those 2 images. So there's a lot of math going on there, or a lot of just really understanding how your software, your algorithms work, and kind of figuring that out. And as we've installed these hundreds of cameras now, we've kind of have to do a little bit of figuring that out in the field, because you might not know exactly where those cameras can be placed until you're out there on especially in we're putting them out in asphalt plants, and you say, I'm going to put it here, and then a site manager might say, well, unless you want a truck to run it over every week. And so, trying to figure out where can we put these, that has been something that we've, so we need someone like Jared, we need someone like you, who we can have on the phone saying, I think we're going to put the camera here and here, and kind of plan it ahead of time, and you give us confidence that that's going to work. Definitely. So that's very interesting. And then I've also noticed with these, there is still limitations no matter what. There's if I'm going to put a camera in a specific positions, and they're going to say both cameras looking primarily north facing, or let's say east facing, you're going to have a problem with the sun at one point. So there's going to be times where that's just not going to work, or you just have to have a very good camera. So can you talk about that? Is when you're setting up a system, or you want to scan something, you have sun in your face. I always like to equate this. We've all taken photos of people at sunset. I'm at the beach. Get my picture. Sunset's beautiful, and you take the photo, and you have 2 options. You either have the background that looks nice, and the person is a black silhouette, or the person looks great, and the background's just blown out all white. Unless you have a really good camera. And I can tell you the iPhone 13 and the 12s, they're doing really good with handling that dynamic range, but most cameras can't. So when you're
you're doing that 3D reconstruction, and you have to be forced to look in the sun, because this is in the wild. This is not in a studio. This is not inside. This is out. What, like, would you always just default to get the best camera possible, or like, what would your suggestions there? I know smartphones is a good suggestion because they computationally can figure that out, I guess. I don't know what they're doing. They're bracketing and taking images. What are some techniques you could do there?
Yeah. And so some of that, you said, okay, yes, like, getting a better camera can help. Like, yeah, if you'd have a camera that has a higher dynamic range and you can expose, that backlit subject more ideally, then yes, that does help. Because at the end of the day, the thing that you want to, the object in the scene that you're trying to reconstruct needs to be, I say, well lit. It can't be completely underexposed or overexposed, because then you're sort of losing out on that pixel data, and won't be able to reconstruct it. So yes, better cameras can help. Also, there's just different techniques can help that. So moving the camera in a different way that tries to have that sun, or that bright light out of view, or hide, like if you're saying trying to take a picture of a person or an object, well, like hide the sun behind the person, kind of get a little bit closer to the person so the sun's hidden, or just maybe try to do it on a different day. Wait till the sun is higher up in the sky. The best day a lot of times for scanning is, on a cloudy day where you have sort of nice, even illumination. There isn't any hard shadows. There isn't any bright sunlight. You kind of have sort of this nice, even lighting. So trying to plan out when you're going to do that scan also goes a really, a far way, because in some situations, the best camera is still going to give, a suboptimal result because there's just so much light coming in, or if it's too dark. If you're trying to do it at nighttime, cameras are really, really going to struggle. You're going to have a lot of noise, a lot of underexposed images or blurry images that even the best camera may not give you great results.
Yeah, I say never underestimate the power of just putting your hand out in the scene and covering the sun if it's in the corner and you just can't get it out, and you can move around, and guess what? If your hand becomes part of the 3D reconstruction, you can always remove that later, as opposed to the scene being completely washed out. I've done that, or a clipboard, or sometimes that's just that sun is just, that's why you have if you have a nice camera, you have the lens hood that will help block out those extra rays. But guess what? You can, given a smartphone, if you're watching on the YouTube video, I have this technique. You just stick your hand right on top of your phone, and it creates your own little sun shield, and you can just put that right around there, and it'll cut out a lot of the sun. So, okay, so that's interesting. So that the last part of this show, I just kind of wanted to talk about practical tips, and I think you covered a lot of them as we've talked. And I just want to kind of go over a couple problems that you will run into if you want to scan things outside, and it's just kind of what you either have to think about ahead of time, or you got to figure out how to troubleshoot while you're in the scene, or perhaps buy better gear. But we'll talk about them and just kind of get your reaction to each one and what you suggest. So I was going to start with lighting, and you did a really good job already addressing that. I always say if it's cloudy, it's like the best day there is. However, I'm in Oregon, and I've been in all sorts of places where when it's really dark clouds, it also can be just poor lighting. So, if you can get the high overcast, the sun's still kind of beating through the clouds, but it's not direct sun. That's your go-to time, if that's when you want to reconstruct a thing. But perhaps thinking of stockpile reports customers, they got to do it the day they got to do it, so they got to make do. So you suggested, picking noon or whatever solar noon is, right?
Yep.
You suggest blocking out the sun, or there's angling techniques, right? So you can, instead of looking direct, you don't have to always look directly at the subject, right? You can kind of capture things at somewhat of an angle and still get a good 3D reconstruction. And that might be all you need to keep that sun out of the way. Or using, I've also found, after doing, thousands of 3D models with stockpiles, sometimes the morning before the sun is kind of in the sky, it'll be bright enough, and you will have the pile or the subject, whatever you're scanning, blocking the sun just because it's kind of like low on the horizon. So that's something to think about. But again, your lighting might be kind of poor, so it's got to be still bright enough. There's probably about like a 30-minute window you can kind of get away with some of that. Okay, so then another one is distance from objects. So now if I want to, let's say, scan a building and it's not safe for me, well, for one, you got to get far enough back to get the subject, and like you said, repetitive structures. You want to get far enough back to get context, but maybe you're too far back. It's not possible. Do you? Is there a problem with just going with the super wide fisheye lens, or should I figure this out a different way?
Yeah. So the problem with that super, like if you have a fisheye lens, those can be challenging to reconstruct sometimes, just due to all the distortion. There's ways to generate a camera, a lens calibration and undistort those photos before using them. But sometimes even then you lose a little bit of visual quality, just because you're trying to take these distorted pixels and then undistort them, and so pixel gets stretched and squashed in different ways, as opposed to using just a more normal lens configuration. But yes, a more like a wider angle lens, like even on the iPhone, you've got sort of, if you have the iPhone, 12 or 13 Pro, where you've got the selection between the telephoto, the wide, and sort of the ultra wide lens options. Just using that sort of wider lens can be helpful in tight situations, just to give you that greater context when you're trying to scan, that full building facade. Other times too, just being careful about your capture pattern. If you're trying to scan a facade, scan a building, you don't just want to walk up, and if you can't see the whole thing in one shot, you don't just want to park there and wave your phone around and look at it from different angles. It's, again, just, how do you move? You want to move the camera. And so, let's start with the first floor and, first story of the building, and walk across, capture imagery of the first floor, and then, and go and say, okay, now I'm trying to focus on the second floor and capture kind of photos, as you walk back and forth, seeing it from different angles and trying to make sure you have enough overlap between those different things. But yeah, if you expect that there's a lot of repetitive structure, a lot of the same windows, the same pattern, the same, things on that, just trying to get further away using that wide angle lens can really be helpful.
Yeah, interesting. And I've noticed that, like a GoPro with their 120 degree lens, something like that, you can get away with that pretty well. Pretty good. I actually like to tell it to, you can distort it or undistort. I find when you kind of have it already undistorted, it works pretty well, but you lose a little bit. It crops out, I think, some of the distorted edges, but even then, you still got a pretty wide view. And also the iPhone, the really wide, and I'm sure the Samsung and all the other Google, they all have these extra wide views. Those all tend to be good. Can you talk about that too? Not all lenses are the same. So as I've also looked at other lenses, I noticed the wider they are, they tend to have more distortion around the edges, and that can be a problem, right? Is that it's not just like, hey, I found this really cheap 16 millimeter lens for my mirrorless camera, let's go for it. I can get tons of the building. Could that be a problem? Is that distortion something we can just overcome, or is that just like really we should, you should learn about what works, or maybe try it and then return it if it doesn't?
I mean, at the end of the day, sure, you always have to try it and see what works. But I mean, the reconstruction techniques, are attempting to compensate for distortion. So one of the process, as part of the process of doing the 3D reconstruction, the computer vision algorithms are trying to estimate characteristics of the lens, trying to figure out, how much distortion is there in the image, what's its behavior, and it uses various, mathematical formulas to model that lens and model its characteristics. But there are cases when you have just, a really poor lens that has sort of uneven distortion throughout the image. Maybe the left side of the image is more distorted than the right because that lens is sort of off center from the camera, or isn't actually parallel to the sensor plane itself, the camera sensor and the lens. If those are tilted or misaligned in different ways, you can get uneven distortion throughout the image, which then becomes a lot harder to estimate during the reconstruction process. And so what that can cause is just the pixels along the edge of your image aren't as useful, or maybe can't even be used at all, because when the computer vision algorithms try to use those pixels to triangulate points, they don't line up because they're distorted, and things just aren't lining up mathematically, and so you end up sort of losing the benefit of having that.
I've definitely seen that on I use a 200 degree lens, and it definitely cropped it. I think the edges, after I did the lens calibration on each lens, and I had several lenses like that, it was actually one of those 360 cameras, and it definitely cropped off specific sides of them. But still, even with that, I got a pretty wide view, which was great. Okay, so that's good to know. So get a good wide lens if you can, if you need to be close to a subject. Be smart about your capture strategy. I like that. You kind of like grid off think of whatever you're capturing, grid it off, start low, move your way up, work your way back down. That sort of thing. Also, I always recommend to people, if they can get access to these free drone capture apps, you can see the patterns that they create to capture 3D models, and you can mimic that with your feet and your hands, and just with the camera in it, and just walk and like, okay, they're gonna grid off. It's looking down, perhaps. Well, I'm looking straight on. I'm just gonna mimic that exact same captures, but the difference is the camera's pointing straight, horizontally, but you can still kind of do your zigzag up and down, and all that. You could I always like to say, copy what they're doing, just apply it to a different direction.
Yep.
Okay, so then when I'm also out there, I notice let's say I'm doing, like you said, repetitive structure buildings, are those new nice shiny steel buildings with lots of glass. You can have lots of reflections. What happens if you have too much reflection? Is that what's happening there? Why would that be something to be really concerned about?
Yeah, reflections are challenging because a lot of computer vision reconstruction techniques assume that a point in space has a constant appearance no matter what direction you're looking at it from. It's because, and that's coming down to this task where we're trying to figure out, when I say we, again, the computer is trying to figure out which pixels match to which other pixels in between two photos. So I have the photo of the wall from two different angles. I'm trying to figure out, okay, well, hey, this pixel in this image matches to this point in the wall, which then matches to these pixels in the other image. Well, if that wall all of a sudden is reflective, when in the first photo, when I look at the wall, it may be one color or one appearance, but I look at it from the other photo from a different direction, the appearance of that wall is dramatically changed based on the reflected light that's coming now from a different angle. And so it makes the task of figuring out which pixels are the same between two photos much more difficult, or even impossible for certain techniques, just due to that changing appearance. And so, reflective surfaces, are pretty challenging for computer vision.
Okay, well, that's good to know. I can offer some strategies around that as well. So obviously, it can't track the surface because it's just changing. That's why water also doesn't work. It's just the appearance of it is moving and reflective at the same time, and transparent. So all those things are bad. One thing that I've noticed a lot of people say is they can use just specific sprays that you can spray something and then it adds a matted finish to it. And then after like hours to 24 hours, that spray just kind of disappears. That's for like vehicles, obviously, things like that, windows. I also personally have seen people scanning interiors with windows, and they just cover the windows with like these masking tape and like drop cloth paper that you use for painting, and just cover them up with paper. Something that's, hey, you don't care that, not like you're going to capture that window or that mirror in a bathroom if you're doing an interior scan anyways, might as well just cover it up. And then lastly, what we've also used is LiDAR fusion. So it's not always works for everything reflective, but Jared, like think of a car. You got a glossy reflective car, that active sensor, using an additional sensor source to get depth maps to figure out that surface. You've used that as well, is that correct? Yep. Something we use is the LiDAR. So here at EveryPoint, we have several apps now that are utilizing that LiDAR. So you don't have to think twice when you're scanning a car of, is this too reflective? It does a really good job at still recovering that in mix with the photogrammetry, the photo-based data. We have all these different sensors you can mix and match to get that. Okay, so we had lighting, reflections, repetitive structures. We've already talked about that at the start of the show. Just think about how you're capturing, get more context, and then obstructions. This is kind of like the last one. As I'm thinking of obstructions, you're going to be outside again. You can't tell people not to come around this area. You can put caution tape up, I guess, if it's like your own site. So you're doing your warehouse, and you're like, hey, this is off limits for a few minutes. But as you're reconstructing something in 3D, what happens if someone walks through the scene? Like, they're not staying still, or like a forklift. So you're in a warehouse, and a forklift just drives right on through. What happens?
Yeah. So a lot of times, using I say traditional 3D reconstruction techniques, structure for motion, the point cloud-based reconstruction things we've been talking about here. When you have a moving object in the scene, it just doesn't even show up in the reconstruction. And that's because, similar to what we just talked about with reflections, where reflections, the reconstruction is it assumes that each point in the space has a consistent appearance. Another assumption it's making is that each object in the scene, it's not moving. So it's only recovering the static parts, the unmoving parts of the scene that have consistent appearance. And so if you had, a truck or a vehicle or a person that just is walking through the scene, you won't see that person reconstructed in the reconstruction. The exception to that is if they stand in place, if they stop, if that car or vehicle stops and stays there for a while, and if you have multiple photos or video frames of that, then you may start to see that object appear. But yeah, typically you won't see it reconstructed. Now, another exception to that is, let's say that object, if you're walking down the street and a car drives by and you keep walking at the same time, well, if that car and you are walking at similar speeds, there may be a whole part of the scene that wasn't captured in your video or captured in your photos due to that occlusion. So you're going to be missing parts of the scene there if that object obstructed part of your view.
Yeah, and you bring a good point of like someone walking into your scene as well. I've noticed, again, anecdotally, they just like to stare at you and, what are you doing? Get out of the way. Get out of the way. You're in the scene. However, if you're trying to, there's all these fun apps now that are using photogrammetry, right? I think like Scanamaze or Point Precise. There's a bunch of different ones out there now for iPhone you can use, and Android, or just on the desktop. And I think it's always fun to scan a friend or scan a family member in a cool scene, and you want to get everything around them. I've noticed that people get wiggly and they start to laugh, and so that's why it's really important for them to stay as still as possible, even like hold their breath, because if they move, things get blurry, things don't show up. If they move an arm, they might have no arm in the end. So, but it's always fun to do those. So I always say to people, we can't stay as still as you think. For one, we breathe, so we move a little bit. So if you can be fast, stay still. And then again, if you're doing like a building, something like that, yeah, maybe you can time your shots between traffic. But if it's moving, you can always take multiple shots from one spot too. Hey, oops, something's in the way. Take it again. Yeah, that one image where that one object was in, that won't be included. So that's good to know. It just includes whatever's behind it though. So we can't use that image to reconstruct something behind it. Yeah. All right. So I know I've kept you for nearly an hour here, and anyone who's been watching this, they pretty much, they can skip going to college and learning about computer vision because they're going to learn it here. But, well, not quite. But anyways, there's a lot of practical tips here. And I guess one thing I didn't touch on, I don't want to spend a lot of time on, but there's cameras. I always am a big proponent of smartphones. I don't think people realize how good even like an iPhone 8 is, or like or a Samsung Galaxy S20 or like several years ago phone. You don't need to have a new phone. You just have to have a phone, and you're good enough to start capturing things in the wild, video, photo, as well as there's these high-end. I almost tell people not to buy a high-end camera unless they know what they're doing, right? I'd say maybe learn with the phone, but when it comes to drones, I suggest get one that you can program, because you can take the burden of capturing right out of your hands and just say, here. So like I don't like to just call out specific brands, but a couple that I know are good there's like the DJI Air 2S has just added the ability to program flights, and that drone is not over $1,000 now. I think it's still under $1,000. I could be wrong. You can get them used. And then there's the Skydio, that as well. You can pre-program that. That's a great drone. I know there's Unique. There's a bunch of other brands. So I'd say if you're going to use this for work and you want to actually get good results, you can manually fly a drone, but you got to know what you're doing. And at that point, you probably don't need to watch this. But I always say go with, spend a little money to get a good enough drone to capture it. But also just know that a sub $1,000 programmable drone, the DJI one I'm talking about, or the Skydio, both have phenomenal cameras. So you're not gonna have an issue with the camera either. It's you don't need to spend thousands of dollars to get in with useful drones. Could I do 3D reconstruction from like I don't know, a really old point and shoot camera that I found from 2012. Probably. Is it good enough, Jared?
Yeah.
Yeah.
I mean, that's the thing. So much of 3D construction. Yeah, like you said, as long as you have a photo, and put a little bit of effort into, planning out your lighting, planning out your capture pattern, that makes a lot more of the difference than just the specs of that camera or the lens that you were using.
And if we looked at your papers, I mean, the 100 million Flickr images, I can tell you were from either 2015 or earlier, and I'm sure there was lots from before that. And there was probably a lot of garbage that still had useful data in it. So just learning the capture pattern. So with that, I think we'll conclude this episode. I think next episode you already told us what we should be doing. We should be talking about capture strategy for reconstruction in 3D. I know there's a lot of computer vision that we haven't even talked about. We've just been mainly in 3D reconstruction world, but if I think we do this episode plus the next one of what's capture strategy, I think that people will learn basics to go out there and go capture something. And there's a lot of good resources online, but if they can come here and learn something from us, especially from a computer vision expert who has taught me a lot. I think anyone can go out there and start capturing and learning to hack things at their own rate, at their work, or for fun.
Yeah.
So thanks everyone for coming. Again, this will be posted on our EveryPoint YouTube channel. You can capture this, or you can listen to this in audio format on basically all the podcast formats. There's gonna be Apple, there's Spotify, there's Google Podcasts, all those. We'll have them all out there for you guys. And please provide your feedback. Let us know if this was handy. We went much longer than we have in the past, but from feedback, people wanted more. So we decided, let's make these shows a little bit meatier, a little bit longer, and see what people can get out of it. And so if you heard something on the podcast, please, and you want to see what it looked like, that video, just go find us. Go search for the word EveryPoint, all one word, on YouTube, and you will find our channel, and you will find this posted there as well. And in the show notes, I will link some of the papers Jared has worked on, and just some of the things we mentioned. So if you want to look for a camera, I mentioned a few drones, things like that. I'll put those in the show notes as well. So everyone, thanks Jared for your time. Thanks everyone who listened and who watched, and we'll see you guys in the next episode.